All right, so my Calc 1 little babies, we are in Chapter 3. We are actually in Section 5, not Section 4. And the topic is limits at infinity, okay? And the way I'm going to start this lecture, let me start with the idea of a horizontal asymptote, okay? And we're going to start with the precalculus notion of horizontal asymptotes. And then we're going to start to build and start to formalize some of these precalculus ideas. But before we do any of that, let me give you an example of what I mean by a horizontal asymptote, right? So take the following the following cost function, c of x. Right, so the total cost for your, let's say what the units that you produce or the service that you provide is the costs are going to be equal to the sum of either fixed costs or variable costs. So a fixed cost might be your warehouse lease, right? Whether you make anything or not make anything, you're going to have to pay that lease payment at the end of each month. And then you have a variable cost, right? Now the variable cost might be if you have an employee and you have to pay them per hour. Well, that cost is going to vary depending on how many hours your employee works. Okay, so let's create a fictional scenario, right? Let's say that after you watch this video, you decide to rush out to, I don't know, Lowe's or Home Depot or somewhere, and you decide to take an investment of, let's say, $1,200 and purchase some equipment to start mowing lawns, right? So an investment of $1,200. Maybe you're going to focus on just small lawns, so you buy, say, a 21-inch push mower and a trimmer and a few other things, and you've done some math, and based on the engine size or and such of the little push mower that you've purchased, that you think that the variable costs are going to be about $5 per, we're going to say, per lawn. Okay? So in this case, X is going to be equal to lawns mowed. Okay? So in a business course, you might ask something about, let's say, a break even, where your revenue is equal to your costs, and that would be where you break even. So for example, you spent $1,200 to get this business off the ground. So I don't know what you're making per lawn, but you're going to have to mow a few lawns to get that initial investment back of your $1,200, right? Now, what we're going to do is we're going to introduce the idea of the average cost. All right, so this is going to be average cost. And normally what they do in mathematics is, or in most subjects, is they put a bar over the function to represent average. Okay, so average. Now, the average age of people in your household, I would have to add up all the ages for everyone that's in your house right now, and then divide it by the number of people that are in your house, right? Likewise, the average cost would just mean your original cost function divided by X. So we have $1,200 divided by X plus, well, 5X over X, right? So that would just be plus 5. I'm going to get rid of the dollar signs just so they don't clutter my workspace here. All right, you ready? So you start off with a cost function of $1,200 plus $5 per lawn, and now you have a average cost of 1,200 over X plus 5. Got it? Okay. So what do we think? How do we think about the average cost? So we're going to do a couple of different things. We're going to look at some scenarios where you start mowing lawns, and we're going to look at your average cost as X increases. Ready? So the average cost of that would just be, your average cost that you incur per lawn. That's what we're trying to say. So ready? Let's say that you're out there, you get this business off the ground, and you get out there and you mow one lawn. Right? All summer long you mow one lawn. Now, what was your average cost? Well, obviously you would have to plug the X value that we chose in for this function. You'd have 1,200 over 1 plus 5. You'd have $1,205 was the average cost per lawn, right? That's a pretty darn expensive lawn to mow. I hope that you got paid a lot of money for it. But now let's start to increase the amount of lawns that you're mowing, right? So now you went out and you mowed 10 lawns. So now you're plugging 10 into your cost function. Well, in that case, you would have an average cost of $125 per lawn. Okay, but again, you get at it, you get busy, you get motivated, you mow 100 lawns that summer. That would bring your average cost down to $17 per lawn. Now, I don't know how you do this. I don't know if maybe you put some headlights on your mowers and you're mowing at nighttime. But somehow, let's say you get out there and you mowed 10,000 lawns that summer. Right? What would your average cost be? So at that point, it would be $5.12 per lawn. Now, all of this, because remember, the topic right now, it's a precalculus and intuitive look at horizontal asymptotes. But all this to ask the following question. Ready? If you keep letting X get larger, right? What is your average cost function approaching? Let me rephrase that. Is there a certain amount of lawns that you can mow where your average cost function would be 0? Is it ever possible for you to get your average cost to be 0? Well, that is a horizontal asymptote question. That is a question about end behavior. So I'm going to do just a rough sketch here. And what you would notice is that, so this is cost over here, and this is lawns mowed over here. Then what you would notice is that in the beginning, your average costs are very, very high, right? But as the number of X values starts to increase, what you notice is your average costs are starting to fall. The question that I had, though, was whether this is going to fall to 0. So if you don't mind, let's take a look at this average cost function. Is it possible for you to ever make that 0? Well, no, right? Because no matter what, it's always going to be plus 5. So what's going to happen is over time, your cost function is going to approach 5. There is a horizontal asymptote. There's a horizontal asymptote at 5. In other words, over the long run, right? I believe it was Keynes said in the long run we're all dead, but in this case, the point that we're making is in the long run, your costs are really your average cost really just become your variable costs. And that makes sense because when you first bought that lawnmower, your average costs were really high, but after you've mowed thousands of lawns with that same lawnmower, right, that the average cost to keep mowing is decreasing, but it doesn't decrease forever. There is a horizontal asymptote. Now, let's go back to precalculus for a second, right? And precalculus, we were given methods of how to find horizontal asymptotes. But the methods are somewhat gimmicky, right? Like I teach Calc 1 all the way to differential equations, but I also teach precalculus every now and again. And when I teach this horizontal asymptote topic, it kills me in many regards because the way that I have to teach it is somewhat gimmicky. I don't get to formalize why the method works. I just get to show them a method. So let's revisit that, right? So what I have here is, now this is just some rational function, and this is ax to the power of n. Now I chose the letter n because it's in the numerator, okay? Over b times x to the power of d, and I chose d because it's in the denominator. And the way that we did this in precalculus was we're going to look at the degree of the numerator compared to the degree of the denominator. Right now, a loose definition of a working definition of degree is that it's the sum of exponents over the variables, but please don't dwell on that yet. I'll come back to that when we do an example to show you what I mean. But here's the main takeaway. If the degree of the numerator is less than the denominator, okay? The degree of the numerator is less than the denominator, then there is a horizontal asymptote at y equals 0. If the degree of the numerator is larger than the degree of the denominator, then there is no horizontal asymptote. Finally, if the degree of the numerator is equal to the degree of the denominator, then there is a horizontal asymptote, and it simply exists at y equals, let me see, how do I want to put this? Yeah, I'll just write it this way. It's going to simply exist at y equals sum a over b. All right, now I'll show you how to do this precalculus method just a second. But don't you agree that this is kind of gimmicky? Like, why does this work? Like, why do we get to simply say that if the degree of the numerator is less than the denominator, we just get to automatically say there's a horizontal asymptote at y equals 0, and so forth? Well, I want to practice this method, even though this is not a precalculus class. I want to practice this method, and then I want to come back and I want to formalize it with some language of calculus. Ready? So what I have is I have 3 functions. And we're going to find the horizontal asymptotes of each of them. Now, I've already produced the graphs up here, but we'll get back to that in just a second. I'm going to go through and we're going to pretend that this is precalculus for just a second. And let's find the degree of the, actually, I'll write this right beside it. So the degree of the numerator, the degree of the denominator. We're going to do this for each of them. Change my color here. Okay, ready? So we defined the degree as the sum of exponents over the variables. Now, in this case, let's you and I agree that in the numerator, the only variable that exists in the numerator is x. And what is the exponent of that? Right, that's just equal to 1. Let's keep going down the line with numerators. Ready? So now, looking at the numerator here, we see that there's only one exponent that has, or there's only one term that has a variable x. And what's the exponent? 2. All right, and let's do this last one. I don't like having this. So let me see if I can move this a little bit over. Let's see if this works. And last, for the last numerator, we have a 3. Let's do the denominators. So we have the degree of, forgive my dog obviously is barking because he sees a cat or a squirrel outside. So that is important to him. And so we'll just let him continue to bark. And for each denominator, the degree, there's x squareds, x squareds, x squareds. So it's 2 for every one of them. Okay. So now let's go ahead and you and I agree that in this case, the denominator in the first example has a larger degree than the numerator. In the second case, the degree of the numerator is equal to the degree of the denominator. In that third case, the degree of the numerator is larger than the degree of the denominator. Now, what were the statements that we were able to make? So let me kind of go back, okay? So I'm going to copy this down. So we were able to say that if the degree of the numerator is less than the denominator, the horizontal asymptote is at y equals 0. And we were able to say that if the degree of the numerator is larger than the degree of the denominator, then it does not exist. And that last one, this last case, when it's equal, is the only time we have to even roll our sleeves up. Ready? So let's go ahead and finish this up. So given that the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote is at y equals 0. Let's look at that graph. Look at what your graph is approaching as x grows really large, right? As x goes to infinity, look at what your graph is approaching. It's approaching 0. All right, let's go to the very last one. So the degree of the numerator is larger than the degree of the denominator. We say that it's not applicable. There is no horizontal asymptote. And look at the geometry. Look at how this bears out. So as you keep letting x grow larger, as x goes to infinity, what does your graph do? Is it approaching a line? Is it approaching a horizontal line? No, your graph is also going to infinity, right? This might be a slant asymptote, but there's no horizontal asymptote. All right, now the last one is the only time you have to roll your sleeves up, and that's if the degree of the numerator is equal to the degree of the denominator. And as I said, what you're going to get is we're going to take the leading term. Look what I'm boxing in here. So the leading term of the numerator, the leading term of the denominator, and we're simply going to divide them. So y is going to be equal to 2x squared over 3x squared. And remember I said that it's going to end up equaling some, y is going to equal some a over b. So the x squareds are going to cancel out. So that leaves you with 2 over 3. So y is equal to 2/3. Notice that, look at the geometry. Notice that as x gets really large, as x goes to infinity, your graph is starting to approach some value. And that value is indeed 2/3. All right, so that is the precalculus way of doing horizontal asymptotes. I like it, right? I like it, but I don't like, maybe you're different. I don't, but at some point in time, you're going to have to stop trusting people with red pens and expo markers, right? At some point in time, we want to know why it works. Now, the way that we're going to do this, and so since if this were a lecture class, I would kind of go through the epsilon definition of limits. But because this is a video, because I don't have access to all the tools that I would like to have available to me, let me start with just, I won't go through this definition of limits at infinity, but what I want to do is make sure we understand the definition of a horizontal asymptote, right? So, as I said, I'm going to get rid of this formal definition of limits at infinity. Definitely not because it's not important. It's just because these are online tutorials and I don't have the time nor the nor my normal resources that I have available to me at college to teach it. So we're going to just look at the definition of a horizontal asymptote, right? Okay, so look. So notice now that you have the language of calculus, you're able to formalize what you mean when you say a horizontal asymptote. So in those previous problems, I kept making statements like as x gets really large, as you let x keep growing, right? But I can, more formally, I can state that. That's basically saying the limit as x approaches infinity, or the limit as x approaches negative infinity. Right, so that so really when we're talking about horizontal asymptotes and behavior, we're talking about limits at infinity. We're talking about limits as x approaches infinity or negative infinity. And notice that when we say that when we made a statement like y equals 0 or y equals 2/3, what we were actually given, what we were actually doing is giving a limit. We were actually finding L, which is a limit, right? So, okay, so in this case, the line y equals L is simply a horizontal asymptote of the graph of f when what? When your limits are approaching infinity or negative infinity of f of x equals L. Okay? All right, let's see if we can use this this picture to show you what I'm talking about here. So notice that there is, geometrically, we can see that there is a horizontal asymptote here. Now, what does, let me see if I can, so in this case, the function, right, I'm just kind of picking up on, we are told the function f of x is equal to 3x squared over x squared plus 1. And what we are going to be able to state is, look, if you want to find the horizontal asymptote, then you could just simply ask, what is the limit as x approaches infinity of that same function? Okay? So now we need to know, how do I actually approach infinity? Right? I mean, what do we do? Do we just plug the infinity sign in for the x? Right? And what do we get? Infinity over infinity? Well, that's not going to help us. So how do we approach this? So let me now go through the technique of what I'm going to be doing on the next page. So what I'm going to do, because I want to take the limit as x approaches infinity of 3x squared over x squared plus 1. What I'm going to do is I'm going to divide, right? I'm going to divide the numerator and the denominator by what? By the highest degree in the denominator. I'm going to say that again out loud, and then I'm going to try to write it. I won't write the entirety of it, but I'll try to give you a little bit in writing. So what I'm about to do is divide the numerator and the denominator by something, and that something is going to be the highest degree, or maybe let me restate it. You could think of it as the highest degree of the denominator. Okay, so we are going to divide, and I'm sorry for my shorthand, we're going to divide the numerator and the denominator by the largest degree of the denominator. And now I don't know that is quite formal the way I said that. In other words, what I'm going to do is I'm going to divide everything by the x squared, right? Because that term, maybe I should say the variable to the highest degree, that leading term. So what does that look like? Well, that looks like this. I have 3x squared divided by x squared over x squared divided by x squared plus 1 divided by x squared. Now, can you follow me that what I did is I just divided everything. I divided the 3x, I divided the s squared, I divided the x squared, I divided the 1. See how everything is getting divided by the same term, right? Everything is getting divided by the same x squared. My dog. Okay, and so what does that look like? So now I have 3x squared divided by x squared, which is just 3. And I have x squared divided by x squared, which is just 1. And then I have plus, well, I'm going to have to leave this as 1 over x squared. Are you with me? Are you along for this ride here? Are you with me on how I got to here? Divide by the x squared. Okay, well, if you are, do you remember me making a statement about what happens if you divide a constant by infinity? Right? Do you remember this in a previous class when I said, look, you are so kind. You have, in this case, you have $1. But if you divide some constant an infinite amount of ways, right? So if you have 1 over infinity squared, you have $1, and you're going to divide it up amongst an infinite amount of people. Do you remember what that equals? Well, that equals 0. Right? If you have $1 and you divide it up by 2 people, each get 50 cents, 10 people each get 10 cents, 100 people each get a penny, but an infinite amount of people, no one gets anything. So this ends up being 3 over 1, right? 3 over 1 plus 0, or 3. And look at what your graph here is approaching. The vertical asymptote, the horizontal asymptote is also at 3. So what is the horizontal asymptote here? The horizontal asymptote is y equals 3, which is the limit at infinity. All right. So where do we go from here? Let's practice this technique one more time. You can kind of look at the theorem here. This is what I was talking about when I said if you end up dividing by infinity, or if you end up dividing by negative infinity, either a constant by it, either way, you're going to get 0 as an outcome. So let's go. This example asks us to find the limit. We're going to start to go through this quickly. So I want the limit as x approaches infinity. Now, what I'm going to do is I'm going to split this up. Right? So I'm going to think about this as the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. With me? Well, remember, what is the limit as x approaches a value of a constant, right? The limit of a constant is just the constant. So it's just equal to 5. That doesn't matter what x does. Y is always going to be 5. Now, as in this other case, this is just like the previous problem. If you divide up something at $2 an infinite amount of ways, this is going to be 5 minus 0, or 5. So if you're asked to find the limit, what's the limit? It's 5. What's the horizontal asymptote? Ooh, y equals 5. That's what this graph approaches. All right, let's now, what I would do is, let's actually go through to those first 3 examples. Remember these guys? When on the first page, I showed you the precalculus method. Let's go back and let's do it again. Now let's use the formal method. And let's finally answer the question of why that precalculus technique works. You now get to formally answer the question. So let's start with what you're going to divide by. So take a look at A. Let's look at the denominator. Are you with me that x squared is the largest degree over the variable in the denominator? Same thing here for B, same thing for C. So are you with me that I'm just going to divide everything up by x squared? So this is going to end up being 2x over x squared plus 5 over x squared over 3x squared over x squared plus 1 over x squared. Okay, let's go ahead and let's clean this up a little bit. So this ends up being 2 over x plus 5 over x squared over 3 plus 1 over x squared. Are you with me? Now, look back in your notes. What did we say the horizontal asymptote was for part A? What was the answer? Well, since the degree of the denominator is larger than the numerator, we said that there's a horizontal asymptote at y equals 0. Ready? Let's take the limit as x goes to infinity of this function. All right, you should be getting a lot of zeros here. Ready? Let's see what happens. So 2 over infinity, that's 0. Plus 5 over infinity squared, that's 0. Over 3 plus 1 over infinity, which is also 0. What do you get? You get 0 over 3. What's the limit? 0 divided by 3 is 0. The horizontal asymptote is y equals 0. Do you see? That's why the method works, and that's always going to be true, right? That's always going to be true if the degree of the numerator is less than the degree of the denominator. It's always going to be true. Okay, let's go to what I'm going to do is I've already told you that you're going to you're going to divide by x squared. You're going to divide by x squared. So what I'm going to do at these next two is just jump to this last step. So that's, you're taking the limit of, well, divide everything up by x squared. Okay, so this one would be, let me just make sure I'm not getting them mixed up on my paper here. So this would be 2 plus 5 over x squared over 3 plus 1 over x squared. Okay, now I'm going to write out part C, and while I'm writing out part C, why don't you think about what the answer to that should be? All right, ready? So when x approaches infinity, what does this function do? Well, obviously, we're going to end up with 2 plus 0 in the numerator. 5 over infinity squared zeroes out. Over 3 plus 0 in the denominator. So you end up with 2/3 as your limit, which was also your horizontal asymptote. Finally, we start going to infinity here. So, all right, with me, I end up with 2. Now, on this stage, 2 times infinity, I still have an infinity symbol here. Now, 5 over infinity, that zeroes out. 1 over infinity zeroes out. I end up with 2 times infinity over 3, or what? Infinity over 3. What does that mean? What does that actually mean? That means you have an infinite rise for 3 feet of run, right? So that's when we say that, okay, there is no horizontal. If you got an infinite amount of rise for a finite amount of run, you don't have a horizontal asymptote. Pretty cool, right? I told you it was probably going to be one of the, well, Matt, I can't remember if I told you it was going to be one of your greatest things you ever did in your life, but maybe that was a previous video, but it's okay. I think you're starting to get it. So I'm going to take a break. When we come back, I'm going to show you some more applications of this technique. Okay? See you soon.